Welcome to CMOS RF integrated circuits. This is the 9th lecture in we are now in module 3. We were discussing passive components. So, in the last class we were talking about inductors. So, we started from the infinitely long solenoid and we deduced our result, what is the inductance of a solenoid. Then we said that as usual we can't really make a solenoid on an IC, and we compressed the solenoid like a spring. So, consider a long spring and you compress it into one surface, right. You compress the entire thing into one surface, you are going to get something which looks like a spiral. So, this is what you are going to get. So, you compress the whole solenoid which looks like a spring into a spiral on one surface, and that is the kind of inductor that we work with on an IC. Then we further went on and we discussed what are the different non-idealities. So, there is a copper loss and there is a core loss. So, both of which we discussed. Because of the series resistance, the wire is also resistive. So, that is why there is a copper loss. An inductor should be lossless, right. It should be a lossless passive component, but instead because the wire is resistive, when a current goes through there is some amount of loss in power, it consumes power. So, that is the copper loss. Then there is the core loss. The core loss was because of eddy currents in the substrate. So, when I have a changing current, because I have got a changing current, I will get a changing magnetic field. Now, this magnetic field, it so happens, will go through the substrate, part of the magnetic field will hit the substrate. Whatever magnetic field is hitting the substrate, that magnetic field is changing. So, the substrate is going to react in a way to oppose the change in the magnetic field. In a way, what it is saying is that the substrate is going to react in a way to oppose the change in the current that caused the magnetic field in the first place, changing magnetic field in the first place, right. So, that is what I need you to comprehend over here. It is a step by step phenomenon. So, I am applying a voltage across an inductor which is changing as a function of time. This changing voltage causes a changing current. Now, I have got a changing current through the inductor, it causes a changing magnetic field. Part of this magnetic field hits the substrate. Whatever part hits the substrate wants to make sure that that magnetic field remains constant. So, it opposes the change in that magnetic field. Now, as it opposes the change in magnetic field, what it does is basically it creates a potential across itself, a changing potential is created across itself. Now, this changing EMF that is created drives a current through the substrate. Now, when I drive a current through the substrate is also resistive, right. The substrate is also resistive. When I drive a current through a resistive thing, it creates a loss in terms of power. Where is this power coming from? Where is this power coming from? Is it coming from the substrate? No, it is coming from the original voltage source that you applied across the inductor, that is the source of the power. It is not coming from nowhere, right. So, we have got a lot of steps in this process, and it is important to understand these steps, because if we understand these steps, then only we will be able to design better inductors with lesser amounts of eddy current loss. Okay. So, it is a non-ideality. Now, then we went further and we developed some kind of a model for the inductor. We saw that the resistance, the series resistance is a series, really the R copper is a series resistance. The eddy currents create a parallel resistance. So, that is modeled over there, and in addition what we have got is the fact that the inductor is not really a pure inductance. You have got a piece of wire hanging on top of a substrate. So, it looks like a parallel plate capacitor as usual. So, that is also part of the model. Then not only that, to make things worse, each turn of the inductor is coupled to every other turn of the inductor through side wall capacitance, right. So, that also is part of my model, and I had lot of those small capacitors between every 2 turns of the inductor. Net result, the model is a mess. I am sorry to say that, but that is how it is. We will have to deal with a messy inductor. Okay. So, now in this class I am going to try to understand, or I am trying to present how do we make better inductors. Okay. So, what are all the different things that you can change and how is it going to affect your performance? What is, first of all, what are the different metrics do we have of the inductor? Number one metric is Q. Thank you. Okay. This is something of great importance. Q kind of summarizes a lot of different things. It summarizes all the different losses in the inductor. How? Well, the definition of Q itself is what? The definition of Q is omega times the peak energy that is stored divided by the average power that is dissipated, right. So, average power dissipated means you have summarized all the losses, you have lumped all the losses together, average power dissipated, and peak energy stored gives you an idea of what is the value of the inductance, etcetera, etcetera. Okay. So, the Q is one of the most important, probably the only parameter of interest, is it? Is there anything else that you are interested in? So, let us go back to the model. The Q kind of summarizes the relationship between L and R copper and R eddy or R core. All these things are taken together and you get a value for the Q. What else is there? There is some capacitance. There are a lot of different capacitors actually, turn to turn capacitance, inductor to substrate capacitance, lot of stuff. How do you model those? Actually, there is something wrong here, right? It should be inductor to substrate capacitance. Yeah. How do you put all of those things in your model? You do not want to make a capacitor that is excellent in terms of all the losses, no losses, but you know there is a huge capacitor, it resembles more like a capacitor than an inductor. Do you want to make such an inductor? No. So, how do we represent what is going to be affected if the capacitance is too large? So, I made a statement earlier which kind of gives you a hint. The capacitance is so large that the entire device looks more like a capacitor than like an inductor. What do you make out of that? What should be the metric? Well, you have got this thing called a resonant frequency, right. You put L and C in parallel, you have got a resonant frequency. So, below the resonant frequency, the device looks like an inductor. Above the resonant frequency, the device looks like a capacitor, right. That is how it is. So, what is the highest frequency at which I can still use this contraption as an inductor? and it does not start behaving like a capacitor. Okay. So, these are my two metrics, performance metrics. Okay. So, one way to optimize your inductor is to have a closed form expression that gives you these metrics and then optimize the different parameters. Well, we are not going to be capable of doing that. To do that, you probably need some kind of an electromagnetic simulator or something, right, or you need to do a lot of jugglery with a lot of equations and then you can work around your way. It is not my business to do all that. What I can offer you is an intuitive feel as to what needs to be done. Okay. So, let us say that this is my inductor. Okay. In last class we were working with a spiral, circular spiral. Today we are working with a square spiral. Any reason? No reason, no reason whatsoever why you might choose one over the other. Both behave perfectly well as inductors. One cool neat thing about the square spiral is that all the coordinates can now satisfy the grid requirements of your foundry. So, the square is quite popular because of that. There are a lot of other varieties of inductors as well, hexagonal, octagonal, etcetera, etcetera. You can choose one over the other depending on what are the different angles that are allowed by your foundry. In this, for example, you are sticking to only 0 degrees and 90 degrees, right, perpendicular and horizontal wires. So, foundries love this kind of stuff. As soon as you start making things at an angle, there is significant risk that your vertices might go off the grid of manufacturability, right, and once they go off the grid you are not sure if the mask making is going to be correct or not, etcetera. So, strange things might happen, that is why a lot of people prefer the square inductor. Fine. Now, assume that okay, let's work our way. What are the different things that you need to do to make sure that the resonant frequency of this inductor is very high? What are you going to do? First of all, you have to reduce the parasitic capacitance to ground. Ground is the substrate. So, to do that, what do you need to do? You need to use the topmost metal layer. If I use the topmost metal layer, then the parasitic to ground is going to be minimized. Okay, fine. Can you do anything else to reduce? No, that is as far away as you can be from the substrate. So, the substrate is here, you use the topmost metal layer and that is the way you can minimize the effective parasitics. What else can I do? Turn to turn capacitance. How am I going to reduce the turn to turn capacitance? You are right. So, basically make the gap between two turns as large as possible. fine. This is understood, this is easy to understand. So, if I increase the gap between two successive turns, the parasitic capacitance is going to decrease, everyone is happy, fantastic. Now, if I have increased the gap between two successive turns, the area of the device is going to increase, fantastic. All right. So, just keep that in mind, that this is a consequence of what you of your optimization. This is the end result, that you end up with large amount of area, fine. Now, the next thing that I want to do is I want to reduce the series inductance as far as possible. So, reduce copper losses. How are you going to achieve that? You have to make the resistance of this wire, the inductor is a piece of wire coiled around, you have to make the resistance of this wire as low as possible. How will you do that? You are going to make the wire as thick as possible. Okay, can I change the length of the wire? Well, changing the length of the wire amounts to changing the value of the inductance. You get a, I mean, if I make less number of turns, then you know what, you get different value of the inductance. That is not something that you would like to do. So, let us stick to the number of turns that you need, the inner radius, outer radius, whatever the radius of the core, let us keep that fixed, right. We can only use thicker wires. Okay. What does that result in? That results in the same thing, large area, because now I have made the gap is also large and the wires themselves are also thick. As a result, the area covered by the inductor also becomes large. Okay. Fine. Now, let us try to reduce eddy currents. How will you achieve reducing, how will you achieve that? Let us say let us not say reducing eddy currents, let us say eddy current losses. Any ideas? So, I have got my inductor, I have got my substrate. Inductor is like an electromagnet. Okay, this was the premise of the story, and I have got my substrate over here. So, some of these field lines are also going through the substrate, and the substrate does not want a change in the flux. So, whenever there is a change in the field lines, there is a change in the flux, the substrate is going to oppose that change, and as a consequence it is going to develop an EMF. Okay, that is also important. Okay. So just from the diagram, what is the first thing that you are going to do? How are you going to make this inductor such that you can reduce the amounts of eddy currents? You are right. What you need to do is place the inductor at a height, go higher. So, be as far away from the substrate as possible. Okay. Now, suppose you are already using the topmost metal layer, what else can you do? So, now take a look. The substrate develops an EMF to resist the change in flux. So, suppose it develops, suppose there is a track like this, and the substrate has developed an EMF across this track of volts V. Okay, what can you do about the track such that the amount of power lost is minimum, or what will you do to reduce the amount of power lost? It already develops a potential V, the power lost is V squared by R. Okay, suppose this track from end to end has a resistance R, then the power lost is V squared by R, which means that as R goes up, the power lost goes down. So, therefore, what we do is we use a highly resistive substrate. What is the substrate made up of? The substrate is normally made up of silicon doped with p type material. Now, actually that is not it. If that was it, then life would be good, but that is not it. What happens is that for our digital circuits, there is a phenomenon called latch up. Have you heard of latch up? Probably. Okay. So, to prevent latch up from happening, the substrate is made highly conductive. So, latch up happens because of bad designers who have not put enough number of contacts in the substrate close enough, right. That is why latch up happens. Now, to solve a problem created by bad designers, what we normally do is we make the substrate highly conductive. So, there exist designers who are bad, the foundry assumes that all designers are bad and they will not put enough number of contacts, and therefore, they put an extra layer in the substrate and make it highly conductive. This layer is called an epitaxial layer. So, let me just write it down. So, if you are working on a normal digital process, then it is very likely that they are going to apply an epitaxial layer. On the substrate to make it highly conductive, like a metal. Okay. Now, if you are making an inductor and you have an epitaxial layer, it is bad news, because there is going to be a huge amount of power lost in the substrate. So, typically what we do is we do a couple of things. We block the epitaxial layer. So, that underneath the inductor at least the substrate is not conductive. So, this is done very routinely to make better inductors. There are other ideas as well. People dig trenches inside the substrate and separate the substrate into a lot of different pieces. So, instead of having one huge conducting plane, so if I draw the top view of the substrate, so instead of having one huge conducting plane under the inductor, they dig trenches and isolate portions. Okay. Now, each of these isolated portions are conducting themselves, but because of the trenches the whole thing is not conducting. Now, this reduces the length, I am sorry, this reduces the area over which the EMF is going to develop. So, now instead of a current going over the entire area of the substrate, you have got small currents over small portions of the area. So, you still get eddy currents, but the quantum of eddy currents is reduced significantly. Have you seen this before in any other discussion? Have you seen this? This is commonly used in transformers. You laminate the core of the transformer, you would slice the core of the transformer into a lot of sheets. Okay. These power transformers out there, you will see that the core is laminated into a lot of sheets. So, that one huge eddy current is not going to flow through all of them, they are laminated and isolated from each other. So, in each of those laminae there is going to be a local eddy current that is still going to contribute to eddy current losses, core losses, but there is not going to be a gigantic eddy current going all through. Okay. So, what you have reduced over here is V effectively. You have reduced the quantum of V over there, each loop has much lesser V. Okay. R is also proportional to V, but net result is that the, so the numerator is, if the numerator goes down, if V goes down 2x and R also goes down 2x, then what is going to happen to the power lost? Power lost is also going to go down by 2x. So, that is what happens in this case. Okay. So, these are some of the commonly used techniques. Use thick wires, use the topmost metal layer, use highly resistive substrate. There are a lot of other ideas with respect to inductors. See, making good inductors is very much an art. It is not really a science anymore. Okay. Why? Is because silicon is expensive. So, every time a designer does something new, he and you know it is very hard to figure out whether what the new thing that he has, the incremental change that he has done, has it really given a benefit or not, because you do not really want to do a massive experiment and compare lots of different inductor designs and so on and so forth, right. So, that is why I am saying that inductor design has become more of an art, and you hear about things and you do things, and it has come down to a point where it is no longer, the science behind the design of an inductor is lot of times disregarded. Okay. So, lot of people use a ground shield underneath the inductor. For example, I will just give you an example. Personally, I do not understand why. Let us see what I am talking about. So, I have made an inductor, I am drawing in 3D and I have got the substrate underneath the inductor. Hopefully, the substrate is far away. Now, what a lot of people do is they put a ground plane underneath on metal 1 underneath the inductor. Next step was that they figured out that the ground plane is conducting huge quantities of eddy current. So, to still keep the ground plane, what they started doing was patterning the ground plane. Okay. Why would you do such a thing? Personally, I am not very clear about why. Okay. The ground plane, this particular material is going to be either copper or aluminum or something like that. These have a permeability of very close to 1. Okay. Most materials have permeability, relative permeability of very close to 1. Relative permeability. 1 is the permeability of vacuum. Only materials that are far off from this relative permeability of 1 are iron, cobalt and nickel. So, as long as you are not using any of these 3 materials iron, cobalt, nickel, you are in the range of 1. So, copper is probably a little bit diamagnetic, I am not sure. So, anyway, it does not matter. Putting copper underneath the inductor is not really going to shield your magnetic field lines. If you put iron, then that is going to shield your magnetic field lines. Why? All the magnetic field is going to come and they are going to be going only through the iron and not through anywhere else. It is like iron likes to conduct magnetic fields. A copper ground plane underneath the inductor is not really going to absorb any magnetic field lines. So, the magnetic field will still go just like before. This is going to behave like an electromagnet. This is a little exaggerated view, but okay. Magnetic field lines are still going to be like that, no change because of the extra ground plane. What is going to happen now is that you have probably created a lot of plates in between for the capacitance, for the parasitic capacitance. So, earlier the parasitic capacitance was the capacitance between the inductor and a ground plane, you know, your substrate, inductor and substrate, these are the 2 plates. Now, you have created a new plate closer by. Now, if this new plate is also grounded, then you have actually increased the parasitic capacitance of this. If the new plate is not grounded, then you have other reasons of concern. Okay. You are going to get a lot of different mutual capacitances, which I am not very sure of what to do with. Okay. So, this is having a patterned ground plane underneath an inductor. So, a lot of people do this. Personally, I would not recommend, I would not ask you to make such an inductor, because I am not sure what the science behind is. So, when you read about inductors, my request to you is think about the science, do not get swayed by hearsay, question everything. There is a lot of bogus stuff out there, and lot of papers get published every year about newer and better and with a lot of different claims involved. Most of these claims are not substantiated that much. Maybe there is some truth, maybe the author of the paper did indeed get a performance improvement by 0.1 dB, 0.2 dB, I do not know, and it is really a cause for concern and at the same time thought. So, you have to think about why did the author do this, what is the science behind it, and then you have to take the paper with a pinch of salt, see what is the experimental setup they have, what kind of experiments and comparisons have they done, and what kind of performance improvement did the author get. Is it something that he could have gotten by fluke, as in experiment to experiment, things might be different. Now, you are getting today you are getting 0.2 dB of improvement, maybe if you tilted the wire a little bit it would have become minus 0.2 dB. So, it is not very clear how I mean if someone gives you a performance improvement which is very small, it is not very clear if that is an improvement at all or not, or maybe a measurement inaccuracy. So, please take such papers with a pinch of salt, and my sincere request to you is to think about the science behind and then go for the design. If you think about the science behind, you are always going to get the right answer. Okay. Yeah, so lot of different inductor designs are there in the literature, pyramidal inductors, circular spiral, octagonal spiral. People have put these ground planes. There is a lot of stuff with the ground planes, patterned ground planes, etc., etc. I do not know. Maybe what they are saying is right, maybe they are not. Please think about the science when you read it. Okay, that is as far as I am going to talk about inductors. You will be getting some homework problems with respect to this, and please try to solve these homework problems as well as you can, and that will give you a further feel and understanding of how to make good inductors. Okay. The next important passive component is going to be a wire. And really had this been any other course, a wire would have been ignored, wire would have been treated as a short circuit. We are going to treat a wire as a material through which electromagnetic wave propagates. Am I right? So, that's going to be our treatment of a wire. So, we are working with frequencies that are very, very large, gigahertz typically. So, at these large frequencies, if you just treat a wire as a short circuit, it may or may not work. Okay. So, what is the first thing that comes to mind? What is the first non-ideality of a wire? A wire has a resistance. Okay. So, let us think about a cable, a wire, solid piece of metal, not necessarily metal, any material, length L, radius R, and resistivity of rho. The material has a resistivity of rho. What is going to be the resistance of this wire? It is easy, you take rho, the resistance is going to be proportional to L, and it is going to be inversely proportional to the cross sectional area. And what is the cross sectional area? It is pi r square. Okay. Now, this is easy to understand. Now, what you are not being told over here is that this resistance typically is a function of frequency. Why? Okay. So, if you study your electromagnetic theory, I do not know how proficient you are with your EM theory course. If you do study it anyway. So, I am just going to pick a result out of there, out of the EM theory course. There is something called skin depth. Okay. What this kind of tells you is as follows. It is like this. If I have a wire, let us not talk about a wire. If I have a conducting material, let us say a slab of iron or a slab of copper. So, I have a slab of copper. And I am trying to push a current through this copper. Okay. Now, what the skin depth business tells you is as follows. It basically tells you that the current is not really going to go through the bulk of the copper, it is going to go through the skin of the copper. So, the current is going to propagate, remember the current is at a frequency omega. Okay. Sorry, I forgot to tell you, if it is a DC current, it just goes through the bulk of the copper. The current is going at a frequency omega. So, what the skin depth formulation tells you is that this current likes to propagate through the skin of the material, through the surface of the material, and the depth up to which the current does propagate is given by that formula. Actually, it is not even that, it's like this, that at a depth d, the current is 1 by E times the current at the surface. 1 by E is about 1/3. So, at a depth d from the surface, the current that is going is 1/3 the current that is at the surface. That is what this exact formulation is, but never mind, for our purposes how we are going to interpret this is that all the current really goes through the surface through a cross section of width of depth d, and the remaining portion of the bulk of the copper plate is unused. So, this portion of the copper or whatever material you are using is unused. What are the different things in the formula? Mu is the permeability and sigma is the conductivity. 1 by rho is sigma. Okay. So, if you have something which is perfectly conductive, that is sigma is infinitely large, then all the current goes through the entire bulk of the material is used for current propagation. However, sigma is finite. Fine. Okay. So, in the light of this, what is going to be the resistance of my wire? Well, now current is going to be conducted only on the surface till a depth d. So, it is like you have got an annulus on the surface through which current is going through, right. So, the cross section of this cross sectional area of this is pi r squared minus pi r minus d squared, that is the cross sectional area, and this gives me my new resistance at a given frequency, right. So, given omega you can compute the resistance. So, what does this tell you? How are you going to make wires, nice wires? It's what it tells you is that if you keep making the wire thicker and thicker, there is not going to be much benefit you are going to get out of it, okay, because the current is only going to travel on the surface of the wire. So, what matters as far as current flow is concerned is a larger perimeter. So, if I have a large perimeter, it matters to me because more current can flow, there is more surface area. Okay. So, this is the region where the current is going to go through. Now, that is your skin depth. Let us go back a couple of steps. How does this, what is the implication of this on your resistor design? Well, the implication of this on your resistor design is if you did not worry about this upfront, then you might get a much larger resistance than you expected, right. Also, it means that the resistance is no longer linear. At different frequencies, the value of the resistance itself changes. Larger the frequency, more the resistance, because you get less area through which cross sectional area through which current is conducting. Okay. What does this mean for our inductor design? For our inductor design, this is bad news as far as this objective is concerned. Reduce copper losses. I wanted to use thick wire, but thick wire is all in both dimensions, both as far as the depth of the wire goes as also the thickness of the wire goes, but there is only so much you can do because you can make the wire higher and higher, but you know the current is propagating only on the surface. So, it does not matter. Okay. So, when you work with your inductor, when you design your inductor, please make sure that you have worried about skin depth. Please make sure that you have done some computations to relate, to find out, figure out exactly how much the depth of your skin is, then what is the thickness of the metal that the foundry is providing. So, only after these computations sign off on your design. Do not ignore skin depth. Okay. So, this has the skin depth has a lot of implications for everybody. Right. So, a wire has resistance, and it is not just resistance, it is a varying amount of resistance as a function of frequency. At DC, the resistance is easy to find out. At higher and higher frequencies, it becomes more and more resistive. Fine. So, kind of leads you to believe that the wire almost works like an inductor. The inductor impedance increases as frequency increases, right. Somewhere it rings a bell, and we are talking about a wire whose resistance increases as frequency increases. So, you know, the wire is kind of behaving like an inductor. So, the next step for us would be to find out what is the effective inductance per unit length of a wire. Okay. And to do this, I am going to model my wire, or actually my system, as a combination of two wires, one through which current is going to go, the other through which current is going to come back. Okay. So, I am pushing this current through this wire, and the same current is actually going to loop around and come back through the other wire, and we are going to consider this system where these two pieces of wire are parallel to each other and are of equal length, etc. Why am I picking up such a specialized system? Is there any justification behind picking up this so many constraints, such a system? Well, do you remember your reflections, how you solve Laplace's equations by means of reflections? Well, it is like this. If you have a wire on, if you have a charge on top of a ground plane, we did this in the last class, you have a plus q on top of a ground plane, it looks as if there is a minus q beneath the ground plane, right. So, if you have a lot of charges on the ground plane, then it looks as if you have a lot of equal and opposite negative charges beneath the ground plane. Now, these charges are moving, those charges will also move, right. So, the bottom wire is actually the mirror image of the top wire. Why is that? Because I have in my head, I have a ground plane in between. Where is this ground plane coming from? It is the substrate, right. The substrate is the ground plane in this case. So, I am just going to compute the inductance per unit length of this setup, and in my mind there is a reason why I picked this setup. I hope the reason is convincing enough. Okay. So, how we are going to do this is as follows. First, we are going to find out the magnetic field at a distance from the wire. Let us say at a distance x from the wire. What is the magnetic field? Then we are going to find the flux. So, we find out the magnetic field at a distance x, then we find out the flux over that entire area. Now, you think of a loop that looks like this. You know the total amount of flux through that loop. So, the rate of change of flux is going to give you the potential, the back EMF that is developed, right. So, what is the magnetic field at a distance x from a wire that is carrying a current I? I am sure you have all forgotten Ampere's law. How do you work with Ampere's law? You construct a loop around the wire, right. The amount of current cutting through the loop is I. So, mu naught by 2 pi times I mu naught I divided by 2 pi r, that is the length of the loop, is going to give you the magnetic field at a distance x. That is fine. So, that is the magnetic field of just one wire. The other wire is going to be very similar. We are going to work on the other wire later on. Just remember that the direction of the magnetic field, if I is going that way, then you have got your right hand rule, and as a result of that your magnetic field is going to look something like this. Okay. Similarly, for the other wire also the magnetic field is going to point into the page inside. Okay. So, we are going to stop here and we will do the detailed calculations in the next class. We are going to find out the effective inductance per unit length. We are then going to proceed and find out effective capacitance per unit length, and then we are really going to work on the wire. Okay, thank you.